Okay, AP Chem kids, this is a video on what a titration would look like and how to calculate the pH when we have a weak acid and we're titrating with a strong base that you see right here. The big thing to know about this is that if you are to just add the hydroxide, let's say you take the pH of your acid, you add the hydroxide, you can't just predict what the new pH would be, similar to how we did in the strong acid, strong base. Because we're dealing with a weak acid, and you make, let's say a weak acid makes a strong conjugate base, and you got the hydrolysis reaction going on, there's really two pieces to this problem. You have to do a stoichiometry calculation first, and then you have to do an equilibrium calculation. So I'm going to go through a case study where we're going to build a calibration curve as well. And again, you have a sheet of paper that you can follow along and put these notes in here. This is also in the textbook, which would be a good thing to have and to take a look at. And maybe watch this video a couple of times. But there's two pieces to this. You're going to have to do a stoichiometry problem first, and then you're going to have to do an equilibrium problem. So the case study that we're going to look at right now is we've got a weak acid and a strong base, and I've got 15 mils of a 0.1 molar acetic acid, and I'm going to titrate with 0.1 molar sodium hydroxide. The Ka for the acetic acid is 1.8 times 10 to the negative 5. So I have that information as well. So, if you're thinking about what this really looks like when we're talking about what's in our beaker here. So as I'm looking at this, and I'm going to draw a picture here, remember, because it's weak, so I have a beaker here, here's my burette, and my burette has NaOH in it, okay? I have in my beaker here, I have acetic acid. Now, since acetic acid is weak, most of it is going to stay together. I shouldn't have that H there because I have it here. So it's HCH3COO. So most of that stays together. There's only a small portion, like to the tune of 1 times 10 to the negative fifth, or 1 times 8 times 10, 1.8 times 10 to the negative fifth. So there's only a small portion that will actually dissociate. So if we haven't added any NaOH right here, and we put a pH meter in here, so I'm measuring the pH, I haven't added any NaOH yet. Okay, so that's pH. If I'm measuring the pH, I took it, look at this. This is just a typical weak acid problem like you did in chapter 14. So I'm not going to go through how to do that. This is where you would do a rice table, and you would find how much hydrogen ion dissociates, and through the Ka expression, you would find the hydrogen ion concentration, then take the negative log of it and get a pH of 2.87. You should try that yourself and make sure that that works, because it does. You can prove it yourself, okay? But what's going to happen now if I have that solution, and now I am adding 10 mils of sodium hydroxide onto that 50 mils of acetic acid. So the major species are acetic acid, sodium hydroxide, Na plus, and water. So that's because the sodium hydroxide is strong. It's going to completely dissociate. This stays together because acetic acid is weak and it doesn't like to dissociate very much. So you don't have very much hydrogen ion or acetate ion floating around. So the first thing you have to do is you have to understand that the hydroxide from the sodium hydroxide is going to want to rip off the H from this acetic acid. So here I've got the stoichiometry that's actually happening is that the hydroxide that you added is going to want to rip off the hydrogen ion, and it's going to make the acetate ion in water. So here's the stoichiometry piece. Before the reaction, you had 10 mils, the concentration was 0.1, so you had 1 millimole. Of the acid, you had 50 mils of acid, that was 0.1 molar, so you had 5 millimoles. Now, after the reaction happens, you'll see that you have 1 millimole minus the 1 millimole, so the hydroxide is all going to be consumed. It's the limiting reactant. And as far as how much acid, the acetic acid is going to be left over is the 5 millimoles minus the 1 millimole, which would be 4 millimoles. Now, the reason why there's only 4 millimoles is, think about this for a minute. The hydroxide was 1 millimole. The hydroxide wants to react with the acid, which is 5 millimoles, to make this acetate, right? So it's this water, or this is going to make the water, the H from the acetic acid and the OH from the hydroxide. So if you only had 1 millimole of hydroxide, that means only 1 millimole of acetic acid can be consumed. And so that's why you have 4 millimoles left. 1 millimole of the acetate ion is formed from the reaction. Okay, now the major species then that are in this beaker after the reaction happens is the acetic acid, the acetate ion, the sodium ion, and the water. You have to ask yourself, who's controlling the pH? Who is controlling the pH? Hopefully you guys are taking a look at it, and it's this acetic acid. The acetic acid is controlling the pH. So what you have to do then is write the equilibrium expression for the pH. And that's coming from the acetic acid dissociating into hydrogen ion and acetate ion. And I'm going to write my rice table as I show you here. So this is the equilibrium piece of this problem that's happening. I have 4 millimoles of acetic acid. And then notice I have 60 milliliters. Where did the 60 milliliters come from? That comes from, initially I had 50 milliliters of acetic acid, but now I added 10 milliliters of hydroxide. So now my total volume is 60. I don't have 50 mils of just acid anymore. I have a mixture because I added the sodium hydroxide in here. So this concentration is 4 divided by 60. Here, the acetate that you had is this 1 millimole that was formed over that total volume, which is 60 mils. So completing the ice table, you'll notice that I get an equilibrium expression here, or an equilibrium line. This 0.66 comes from 4 divided by 60. And the 0.16 comes from the 1 divided by 60. So now this equilibrium line can be put into this equilibrium expression. And when I do that, and I can then ignore x, and I can solve for x the easy way because this dissociation is so small, I get a 7.2 times 10 to the negative 5 molarity. That's my hydrogen ion concentration. But wait, we're not done. No, we're not. We still need to figure out the pH. Well, pH is the negative log of the hydrogen ion concentration, and we come up with 4.14. So I believe in your packet you have a space where you could draw the line. So I'm going to just kind of start adding that onto here. I'm not going to do this for every slide, but notice how that pH starts a little bit higher than what it did when we were talking about strong acid, strong base. So the first point that you have is really probably going to be kind of right about there, okay? And we're going to see that pH curve starts a little bit higher. A lot of that has to do with this equilibrium reaction that's going on, okay? All right, so now we're going to continue, and I'm going to take a look at, well, what happens if we add 25 mils, okay? The process is exactly the same, and I'm talking about 25 mils total. So we initially added 10, now I added 15 more, so I'm at a total of 25. Before the reaction, okay, I had 25 mils of a 0.1 molar, my sodium hydroxide, so I have 2.5 millimoles of hydroxide. I had 50 milliliters of my acetic acid, so that's 5 millimoles. I hadn't made any of the acetate ion. Now what happens is I am using all of my hydroxide because I have 5 millimoles of acid. And when I subtract and do this math, do this stoichiometry math, at the end I'm going to have no hydroxide left, and I'm going to have 2.5 millimoles of acid. So we're still in an acid situation. But I've also formed 2.5 millimoles of the acetate ion that's formed during the reaction, okay? Now, the major species that are in place are the same. The acetic acid, the acetate ion, the sodium, and the water. The sodium has no acid-base properties. Water, has a Kw of 1 times 10 to the negative 7, 1 times 10 to the negative 14, so that's not a very strong acid or base. What's controlling the pH is still this acetic acid and the acetate. But what's interesting here when we plug in this information is that we get equal concentrations, if you'll notice, because you have 2.5 millimoles of the acid and you have 2.5 millimoles of the conjugate base, right, the acetate ion. When we actually do the concentrations, you can see through this work that it's 0.033. So when we apply this into the Ka expression, here's the equal, the Ka, we can say that the pH, or I'm sorry, the Ka is equal to the hydrogen ion concentration, because what happens is you'll notice that these cancel each other out. And the hydrogen ion concentration is actually 1.8 times 10 to the negative 5. And if you're saying to yourself, Mrs. Snyder, does that mean that's a buffer? And that's exactly what that means. This is a buffer. And we're going to be talking about them in terms of where they show up in the pH curve. So in the titration curve, you should be able to recognize where the buffer is too, okay? Give you a little hint. It's usually called halfway to the equivalence point. That's where the buffer is. We do this. Notice that pH is 4.74. So it is just slightly higher. I'm going to go back one page. So we're going to go back to what it was at when we were talking about it being 10 mils. It was 4.14. And so now you're saying when I add 15 milliliters more, I'm at 4.74. And what happens at this part of the curve, I'm going to draw it in here again. So here's my curve again. And so if we were to do my first point, which was 4.14, and my second point, and it's about 15 mils more, so I'm going to put it right here, okay? You'll notice that that kind of gives you a really kind of flattened out kind of region, and that's going to be called really the buffer region of the titration curve. So you can look for that as well. All right, I'm going to pause here for a second, and I'll be right back. Okay, I'm back. I just wanted to make sure we could get this this slide done in the same amount of time frame, in the time frame that I have listed, because this is clearly going to be a two-part video on titration curves. The next option is, well, what happens when you add 40 mils total? Process is exactly the same. You have the same major species. What I want you to do is I want you to go ahead and do this work, fill it in, and check your work. So I'm going to ask you to pause right now and check your work and do this and see if you get the same pH value that I get. So this is a good time for you to do that. So just go ahead, pause, start working. Okay, I'm back. Did you get a pH value of 5.35? I did. Hopefully you did too. If you didn't, I recommend checking out your textbook or checking your work carefully, okay? There's going to be another part to this. We're going to get to the next part of getting to equilibrium, the equivalence point, I should say, and also beyond the equivalence point. But I can't do that all in the 15 minutes I'm allotted in Screencast-O-Matic. So I'm going to sign off for now, and you will want to get then to the second part of this video, which will be part 2 of weak acid, strong base titrations. That's where we will start on the next slide. See you then.